exterior angle theorem. So we kind of move on to different relationships within different geometric figures. Right? So the exterior angle theorem, very short theorem, but also wordy enough to be pretty confusing. But we'll get to it in a sec in terms of an example, but I'll just read it right now. The exterior angle of a triangle is the sum of its two non-adjacent interior angles. Like, oh, all right. Things just got real. Right? I'll just give you a quick diagram to show you what that means. First off, we're going to talk about the exterior angle of a triangle. And I suppose the non-adjacent interior angles are probably going to come into the conversation. Also, I'm being like, of course, they're going to come into the conversation. So if I have a triangle, really doesn't matter what it looks like, but then I create, I don't want to shade it in, so I'm going to get rid of that. A line segment extending from the base outward beyond the triangle. Right? This would be the exterior angle. There's actually a bunch of exterior angles. I'm just focusing on one of them, right? Because technically, anytime I extend a line, I create an exterior angle. So this would be an exterior angle. So with this. So with this, but it gets pretty messy and confusing after a while. So I'm just going to get rid of all that for now. All right. So I just focus on one of them. All right. Now you have three interior angles and they're not all necessarily the same size. All right. So I'll call one of these, or I'll give one of these a single arc. And give another one 2 arcs. And another one 3 arcs. And all that means is that there are 3 angles that have 3 different measures, all right, or are not necessarily the same as one another. So each one of these angles are interior angles, all right? So anything in here, so these are all interior. This one, and this one, interior angle. I think that idea should make some sense because you think about interior, inside, you know, like interior of a house or something like that. You're inside the house, right? The exterior outside, all right? Now, the adjacent angle, an adjacent angle is not in contact with the given angle. So 2 angles are adjacent if they are physically in contact with one another. They share a side, right? So I'll give you an example of adjacent angles, and then I'll show you why this works the way it does. But let me just pull this diagram here, copy, paste. So these 2 sides, this one here and this one here. I'll go with 4 now because I've already used the others. All right, these 2 angles, they share a common side. I'm sorry, they share a common side. I almost highlighted the wrong thing. Right? Angles that share a common side are called adjacent angles. Right? So these are adjacent. Right? So what we're talking about here are 2 non-adjacent interior angles. Right? You go back to the theorem. The exterior angle of a triangle is the sum of its 2 non-adjacent interior angles. Right? So I'm talking exterior angle, 2 non-adjacent interior angles. Right? Because these 2 are adjacent to one another. So this guy over here would be an adjacent angle. I want the 2 that are non-adjacent. What this rule is telling me is that if I take the sum of these 2 angles, that'll be equal to this one. All right. So I'm just going to duplicate the diagram one more time. If I tell you that this angle here is 20 degrees and this angle here is 60 degrees, not drawn to scale, so it doesn't look like 20 degrees would be like a little sliver of an angle, but that's not. right? If that's 60 and 20, if those two angles are 60 and 20, and the exterior angle is the sum of the two non-adjacent interior angles, then this would have to be 80 degrees, which really doesn't, again, make sense based off of the picture, but that's what the theorem says. Now, if I drew it to scale, it actually would make sense, but I didn't draw it to scale, so it doesn't make sense, because this does not look like an 80-degree angle. Now, if you haven't played around with a protractor yet, you may not recognize that, but I can tell you that if I draw a vertical line here, this piece here would be 90 degrees, which is more already than what I have written here. Right? But what we get at here is when we draw sketches, they don't have to be to scale as long as the math is sound, right? Because I could get a protractor out and draw this, but you know, it's not going to be the quickest process in the world, right? So that's the general idea, and also it kind of puts you on guard to not fall in love with the scaling of the diagram, because sometimes they're I'll say misleading. You know, something that looks like an obtuse angle may not be obtuse, and something that does look obtuse, you know, or something that doesn't look obtuse maybe. Right. So
Professor?
we have, yeah, question.
Could you do a sample of a non-adjacent, just like you did with the 60 and 20s?
So do another example.
Yeah, but you just did adjacent, so of a non-adjacent, would it be?
Oh no, these are the non-adjacent.
Oh, that is the non.
Yeah, because this angle here would be the adjacent.
Okay, got it.
So you see these complicated diagrams below, especially this section here where you get into all the different angles. You can sort of start to see how you can verify some of the rules that we're going to come up with, but you know, they're very busy looking diagrams, so it's easy to kind of lose track of, you know, what's going on. So we go through our rules carefully, because you want to get a good handle on them individually first. My app just crashed, and then we put it all together, and so it's kind of painstaking, but we get there. You know, assuming my app wants to open up. It always opens up to the wrong page when it does that. I don't know why. I don't know why I can't just go back to the right page, but it is what it is. Right. The angle side relationships. Right. I honestly, I think these might go under the category of, like, I don't want to call it common sense, but I'll say once you think about it, it makes sense. Right? At first glance, you might be like, "Oh, there's a lot of rules here," but then you think about it, and you're like, "Ah, you know what? This one isn't bad." You know, the shortest side of a the exterior angle of a triangle is the sum of its two non-adjacent interior angles. That takes a minute to think about, right? But these should be a little bit easier. Right? The shortest side of a triangle is opposite from the smallest angle in that triangle. Right? The middle length side of a triangle is opposite from the medium angle in that triangle, and the longest side is opposite the largest angle in the triangle. Right? So I'll just draw a quick diagram kind of off on the side. So let's say I'll do an obtuse triangle here. I was hoping it wouldn't shade it in. I mean, I don't hate the shading. It's just I'd rather not be like the boring gray shading. Yeah. So we have three sides here and three angles. Right? The three sides may be the same length, most likely not, but they will be in relation with the corresponding angle. Angles and sides are in relation with one another, right? So this angle here is definitely the largest out of all the angles. If I put a protractor on it, this would be bigger than this angle, and it would be bigger than this angle. All right, but you don't really need to put a protractor on it because it's an obtuse angle. And, you know, there's certain things in geometry that you don't necessarily think about early on, but once you consider it, it makes perfect sense. Yeah, and this, you know, this overall theme is one of those, but you can't have any angle bigger than an obtuse angle in a triangle, right? And you can't have more than one obtuse angle in a triangle, right? So, and that's because all the angles, all three of them have to add up to 180 degrees, right? So if you just think about it, let's say this angle is, I'll just make up a number, is 100 degrees. These two angles, neither of them could be bigger than 100 degrees, because if they were, then you'd have values that add up to more than 180 degrees, right? So I'm just going to make up some values here. We'll say that this one's 100. I'll call this one like, this one looks like it might be a 30-degree angle. And so we'll say this is 50. All right. So I'm going to label it up. We'll call this angle A. We'll call this angle B, angle C. All right. So what this rule is telling me is the relationship between the size of the angle will correspond to the relationship between the size of the sides. Right? And it's a mouthful, but let me just show you. Using notation, I would say the measure of angle B is greater than the measure of angle A, which in turn is greater than the measure of angle C. Okay. All this is saying is this angle's the biggest, this one's the middle, and this is the small. All right. Biggest, middle, small. So when we name our sides in a triangle, whatever the angle is, opposite that angle is the corresponding side. All right, so I have angle B here. Opposite of that is side B. I have angle A. Opposite of that is going to be side A. And opposite of angle C would be side C. Just all lowercase. Capital letters for angles, lowercase letters for sides. All right. So what this is telling me is that side B is going to be greater than the measure of side B is going to be greater than the measure of side A, which in turn will be greater than the measure of side C. I'm using shorthand notation to represent the sides. Right, that little bar on the top is notation for a side. I'm just using M for measure and the lowercase letter to indicate the side. You could also do it with the endpoints where we would say measure of segment AC, BC, whatever. That doesn't really prove my point as much as I wanted to. So you see the relationship is the same. Angles are in a particular order. B is bigger than A, which is bigger than C. So the same relationship has to hold true for the sides. Right? That's what this rule is getting at. Right? So if you know the measures of all the sides in a triangle, then you can determine which angles are the biggest and which ones are the smallest. If you know the measure of all the angles in a triangle, you can determine which sides are biggest and which ones are smallest. All right. But that's only within a single triangle. Right? It's not, you can't compare, it's not apples and oranges. You can't compare from one triangle to another. There's other rules that come into play for that. Right? Unfortunately, they're more complicated. So, you know, that's a thing. But when you look at the first example here, it's the measure of angle ABD. Okay, so ABD, when we name an angle, we just follow the path based on the lettering. So ABD That's this angle here. And BAD. So BAD, I want to make it look a little nicer. Close enough. All right. So these are two angles contained within the same triangle. So I want to know what their relationship is. Right. Well, the two relevant sides would be this side at 35, at a measure of 35, and this side here at a measure of 39. Right. So what I would do here is look at either one of them. It doesn't matter. We look at one at a time. We look at them together. Ultimately, we do it all in some fashion, one way or the other. So it doesn't make a difference. But this is side B because it's opposite angle B. This is side A because it's opposite angle. All right. So what I've just learned here is that the measure of angle B, I'm sorry, side B. Oh, why did it do that? Nobody knows. The measure of side B is bigger than the measure of side A. That's what I got at it. Right. So that means that this angle, so you just kind of follow the arrow back to its origin. All right. So we know that this is the bigger one. So that corresponds with the bigger angle, which was ABD. So that means that the measure of angle ABD has to be bigger. And again, follow this back to its origin, which was angle BAD, measure of angle BAD. All right, so that relationship is greater. Now, it's a lot of detail for a, just a simple pick one. Which one's bigger, determine the name of the angle in which it corresponds to. But it's necessary, at least in the early go. Because once you get used to it, you start looking at it and be like, all right, that one's bigger, that one's smaller, and it's easier. But and also, if you're confident that it's drawn to scale, which I wouldn't be, some people would just slap a protractor on it and say, well, it looks bigger, so it is big, but you can't always count on that. All right. So ADB in number 2. So ADB, this line segment followed by this line segment, giving you this angle. All right. So opposite of that angle is this side here, which we would call D. So D is 23. Right? Then BAD. So they're giving us extraneous information, stuff that we don't really need here. Like all this other triangle and this other triangle is turning out to be irrelevant, but sometimes that happens. Right? So BAD is this angle. Those two line segments forming this angle, corresponding to this side, which we would call A because it's opposite angle A. Right? Now, the relationship between side A and side D, right, is that the measure of side A is bigger than the measure of side D. All right. Now that D corresponded to the ADB. So that's measure of angle ADB. The A corresponded to the BAD. All right. So the measure of BAD is bigger than ADB. But the way they pose the question is the reverse of that. All right. So I would have to think about it and say, all right, well, if BAD is bigger than ADB, that also means that ADB is smaller than BAD. right? It's weird because you write it down one way, but the question's asking for it a different way. And sometimes with inequalities, it's easy to get your wires crossed. I always look at it, I always go back to the simplest way of thinking about it. You know, forget about geometry, forget about just math class. I just think about something very simple like ages. Like my brother is older than me. That's one way to think about it. So his age is greater than my age. Right. So Fred is greater than Ted. Yes, our name's right. Right. But that also means, so he's older than me. That also means I'm younger than him. Right. It's the same relationship, just looking at it from a different perspective. So I'm younger than him. So Ted's age is less than Fred's age. So Fred's age is greater than Ted's age. Ted's age is less than Fred's age. Both mean the same thing. All right. So it's just a matter of perspective. You throw in some crazy notation like this, it makes it seem more complicated than it really is, but it's really not as crazy as it seems. Right. Speaking of perspective, numbers 3 and 4 are going the other way, where we're given the angles and we want to determine the relationship between the lengths and sides. So we're looking for LM, relationship between LM and LP. Different color. All right. So this red side is opposite the angle at this location, LMP, or right at that angle that's located at M. But I can't say angle M because that could mean this angle too. So we want to be very specific when we say the name of an angle. So this would be, I don't even know how that happens. Oh, it's a double tap. That's what, okay. I'll try not to do that anymore, but at least now I know why it's happening. All right, so we'll have to name this one in a sec. But I'm also looking for the angle that's opposite this side, which would be if I follow the path, it's going to put me down over here. So we have a relationship in terms of the angles. So L, if I follow the path, so in order to name it, I'm starting here at L, going to M, and then ending up at P. All right. So angle, the measure of angle LMP. Now this number is bigger than this number. So that's going to be bigger than, now I just want to name this angle here. So pick a starting point, like over here, follow the path L to P to M. So the measure of angle LPM. All right, so that's the relationship between the two angles. All right, now LMP, that's the red. All right, that corresponded to LP. All right, so LMP, that was the red. So that's the measure of line segment LP. Right. And then LPM, that's the blue, that corresponded to this side over here, which we could call LM. All right. Since the red angle is bigger than the blue angle, the red side has to be bigger than the blue side. All right. But again, it's another matter of perspective. I say LP is bigger than LM. That's the same as saying LM is smaller than LP. All right. Now, there is a typo here. These should both have, oh, actually, number one, I don't know why the hell the 18 and 19 are there. So those shouldn't be there. These should both have little m's in front of them. Same thing over here. What I was saying before, equality, inequality, that only applies to measures. It doesn't apply to just line segments. That would be a measure of congruence. All right. So number 4, I mean, you can start doing a little quicker. You know, I tend to, especially with the the formative stuff when it comes to geometry, I tend to really kind of take it slow and easy, as tedious as it might be, just because I want to make sure that we all have equal footing moving forward, because everybody comes from a different background in terms of their geometry preparation. Some people took entire courses on geometry, and some people have never seen geometry before. So, it could be incredibly boring for some people and only mildly boring for other people. No, I'm sure it's riveting. I sprinkle in a joke here and there, so that makes everything okay. Although I don't think it's done yet. So the measure of CE compared to the measure of CD, right? So CD, or well, I'll start with CD first. Right, yeah, CE. And CD is right, right. Now, the issue with this problem, aside from all of this extraneous information, all that information that we don't need, is that I don't have every angle in this triangle, right? But I do know that there's 180 degrees contained within the interior angles of a triangle. So if I take 180 degrees and subtract the two angles I know, I'll take off the 50 first. That's going to be easier computation. That'll get me to 130. And then I'll subtract off the 55. That should get me, if I'm not mistaken, to a 75. So that means that this missing angle here has to be 75 degrees. All right, because all three of those angles have to add up to 180. All right, you don't have to show the computation, do it in the calculator if you want. Okay, so just simple 180 minus 180 minus 50 minus 55, so 75. Right? So the angle that's opposite side CD is the 55-degree angle. The angle that's opposite CE is the 75-degree angle. Right? So we're naming our angles again, following the pathways that make up the angle itself. So if I'm starting here at C and I want to name the angle at E, I'd follow the path up and out, right? So that would be CED. So the measure of angle CED, right? And then I want to name this angle here, so I come in and go out. So that's CDE. You could also say it backwards as long as the same letters in the middle. So the first one I could say DEC, and the second one I could say EDC. All right, as long as the relevant point is in the middle, wherever that angle is, whatever the letter is that represents that angle, that has to be in the middle of your trio of values. All right. Now CED is smaller than CDE. All right. CED is the red. That corresponds with side CD. So the measure of side CD is going to be less than the measure of side CE, because that's the blue here. I know it doesn't look very blue anymore, but now it does. I'll blue it up. All right, so that's the measure of side CE. So CD is smaller than CE, but again, you look at how they ask the question. They want to know the relationship between CE, the measure of CE, then CD. Well, if CD is smaller than CE, then CE must be bigger than CD. All right. Honestly, I have no good reason for why number 5 is here. So you could ignore that. I want that to lock in. this gets at the exterior angle stuff, right? So kind of fun to look at, but you know, there's a fair amount to it. I just don't want to move too far ahead when people are possibly still copying. Take a sip of water. So number 6, we get into polygons and the relationship there, but we use the concept of an exterior angle to help us draw some conclusions about polygons in general, right? So we talked about the idea of the exterior angle being the sum of the two non-adjacent interior angles, which is helpful information, right? But what we want to do here is use that to draw conclusions, not just about triangles, but about other figures, right? Now, when we say something is a regular anything, whether it's a polygon or any kind of polygon, you know, so we have a triangle, we have a quadrilateral four-sided figure, a pentagon, a hexagon, you could have octagon, you could have any kind of gon, right? Nonagons, nine-sided, decagons, you know, like just take the number of the number of sides in the figure and just throw a gon at the end of it, and you'll have, for large numbers, you'll have an appropriate name for a polygon. And so you'll see here number 10 where it says, how many sides does an n-gon have? You're like, oh, wow, this just got a little crazy, right? But just keeping it simple, a regular polygon, all sides and angles are congruent. All right. So all the sides are congruent to one another and all the angles are congruent. So in a triangle, since there's 180 degrees, if I wanted to figure out what one of the angles are in a regular triangle, also known as an equilateral triangle, all I'd have to do is take 180 and divide it by the number of angles. Right? So 180 degrees divided by 3 would be 60 degrees. So each one of these angles is 60 degrees. Now, that's all well and good if you know the total angular measure inside of a polygon. All right. So, I mean, you could take a stab at it for a quadrilateral. I mean, these all look like right angles, and right angles are 90 degrees. So it's a pretty reasonable assumption that they'd all be 90 degrees. But it's like, well, what about this? How would I figure that out if I don't know how many angles, how many degrees there are in total? That's what we're getting to, right? So I know each one of these angles here is 60 degrees. So A is 60 degrees. Now, that exterior angle B, we learned previously, is the sum of the non-adjacent interior angles. So this B here is going to be the sum of these two angles, which is going to make it 120 degrees. All right. And it's also, it's a nice little justification of something that maybe a straight angle is two angles that form 180 degrees, or well, straight angle is 180 degrees. Supplementary angle is what I meant to say. Supplementary angles are two angles that add together to equal 180 degrees. Right. So 180 degrees is the straight angle. Right. And it's kind of weird to think about it, but if I have a point and a line segment emerging from that point in one direction, I could have a line segment emerging from that point in any other direction, right? If I put it up here, that creates a right angle. If I put it over here, it creates an acute angle, an obtuse angle. But if I put it down here, it's still an angle. We saw what I did. I just moved it around, angle, 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 angle. Why would it be any different just because I drew it straight? It's still an angle and it's straight. Therefore, it's a straight angle, right? But if I created another line segment coming out of this point, then it would make sense that whatever these two angles are, they would have to add to equal whatever the measure of the straight angle is. And if you know that that's 180 degrees, then it all kind of comes together. All right. So the 60 plus the 120 here gives you the straight angle of 180 degrees. Right. And that would happen in each one of these cases. If you look at it, in every one of these cases, you're talking about two supplementary angles, two angles that together create a straight angle. Right? It's just that angle is a little bit different in each case. Right here, it's just straight up vertical. And then in other cases, they're acute. You know, you could have obtuse. The first one was the case of an obtuse angle, but that's a relationship that we can rely on. But in a rectangle, now it's a little bit of a different story, right? Because you got to sort of look at it and say, what are my senses telling? What's the obvious? Now, in this case, in a rectangle, we know that all sides and angles are congruent. That's true, and it says it right there, right? But on top of that, we also know that there's 90-degree angles in a rectangle. Right? So they're all what we call perpendicular, but even that word is not 100% necessary at the point. We just know that they're 90 degrees. They're right angles. So each one of these is the right angle. Right? So a right angle is 90 degrees. And so what we learned here in this problem is that two adjacent angles that are put together to form a straight angle are going to be supplements of one another, right? So they got to add up to 180 degrees, right? So that's going to be the same here. These two angles have to add to equal 180 degrees. So if one of them's 90, the other has to be 180 minus 90, also 90. Little formatting issue here. Little tab bar never got hit. So E should be E equals F equals G equals H equals. These are really out of whack. And so, I mean, most people are familiar with triangles and rectangles, but now we're talking about pentagon. And so we want to be able to sort of generalize what we're learning here. The problem is it doesn't seem like there's an obvious scenario that'll allow us to do that, right? There are rules, right? I mean, you can develop a rule pretty much for anything in geometry and any kind of math, but the more rules you have to remember, the trickier things are. I can tell you that the basis of what we're going to do here all comes back to the triangle, right? So if I were to draw an exterior angle, I'm going to just kind of move this out of the way for a sec. If I were to draw one exterior angle at each vertex, once again, there's no good place to put this. No, that's a white marker. That's why nothing showed up. If I draw an exterior angle at each vertex, I'll draw one here, just a single one. It doesn't, you don't need to do more than one. All right, I'll do one here. That doesn't look like much of exterior angle. Close enough. In each case, you're going to get 120 degrees for that exterior angle, regardless of what rule you use. Right? If you use the rule where these two angles have to add to 180, you'll get 120. If you look at this as, okay, here's an exterior angle, it must be the sum of the two non-adjacent interior angles, you'll also get 120. Right? Either way. Right? You'll get 120 over here also for the same reason. Right? The sum of these exterior angles happens to be 360. Right? So let's move on. Fun fact for now. So let's move on to the quadrilateral, or in this case, the square. We know that that D degree measure is 90 degrees. If I draw a single exterior angle at every vertex, at every point along the polygon, and it doesn't matter which direction you go with it, there doesn't have to be consistency. You just need to have a single exterior angle. In every case, you're going to have 90 degrees. The sum of those four exterior angles happens to be 360, right? The sum of the exterior angles of any polygon is always 360 degrees. So that's useful information because if I'm looking at a pentagon, I can draw exterior angles all across the board here. I don't actually have to draw them, but I'm just going to do it just to really drive the point home. If I know that all of these exterior angles together have to add to equal 360 degrees, then to go the other way around, all I would have to do is take 360 degrees and divide it by 5. Right? There's 5 possible exterior angles because there's 5 sides in the triangle of pentagon, because there's 5 points that make up the pentagon consistent with 5 angles in the pentagon. All right. 5 being the active important. So that tells me that each exterior angle has to be 72 degrees. If we know that the relationships, so now I'm kind of working backwards here. If I know F is 72 degrees and the two angles, those two supplementary angles have to add to equal 180, then a quick 180 minus 72 will get me the interior angle, which would be 108. So it's a couple computations, but it's very manageable because you don't have to draw the picture as long as you know the number of sides, angles, etc. in whatever the regular polygon is, you're good to go. So in the hexagon, I have 360. I'm going to divide that by the number of angles, number of sides. Number of angles and sides are always the same in the polygon. That's going to give me 60 degrees. That's going to be my exterior angle. Subtract that from 180, and you get the interior angle, which would be 120. Now, it's not much of a stretch to go a step further and use that to find the sum of the interior angles of a polygon. Right? And that's because you look at it and say, all right, well, now that I know what each interior angle is, I just multiply it by the number of interior angles. Because if they're all the same, that's all I would have to do. So if I know that this is 108 degrees, I would multiply by 5, and that would give me the sum of the interior angles. If I know that this one is 120 degrees because this one was 60. 120 multiplied by 6 would tell me the number or the total, the sum of the interior angles of the hexagon, right? But like in number 7 and 8, we already knew that stuff. That's how we were able to kind of figure everything out. How many sides does a triangle have? Triangle has 3 sides. The sum of the interior angles of a triangle, sum of interior angles is 180 degrees. Right, that's something that we knew. We knew in some cases because I told you, but in other cases maybe you knew it already. All right, the quadrilateral has 4 sides. The sum of the interior angles, we knew that that was 360 degrees. Right, which is 180 degrees more than the triangle. But then they jump right into the fire here. How many sides does the decagon have, and what's the sum of the interior angle of the decagon? It's like, oh, what about the pentagon and the hexagon and the octagon and septagon, heptagon, octagon, all that good stuff. It's not really necessary to get into that because there's an established pattern here, right? Because if I take 180 degrees for my triangle, tack on another side, I get up to 360 degrees. Is there some sort of pattern there? It seems like I'm increasing by 180 degrees for every side that I tack on, right? So I could just kind of investigate that real quick and see what would happen if I took 108 and multiply it by 5. That's 540. So we started off at 180 degrees for the triangle. We added on 180 degrees to get to a rectangle. I'm sorry, in this case, it's square, it's a specific type of rectangle. Tack on another 180 degrees, we get to a pentagon. Every side is worth another 180 degrees. A hexagon, add another 180, I get to 720, which is what you would get if you took 120 degrees and multiplied it by the number of angles. All right, so there's a relationship here, and that's why we need to know how many sides there are, because a decagon, like decagon, decade, when I was talking about decimeter and decameter before, tenths, groups of 10 or tenths units, has 10 sides. All right, that's, if you're starting up with a triangle, you got to go 1, 2, 3, 4, 5, 6, 7 more sides to get you to a decagon. All right, 7 more sides. Then I think I said then a decagon. I meant to say then a triangle. All right, so if we're talking about 180 degrees being the triangle, then I would need 7 more 180 degrees, seven more 180 degree measures to get me to the number of degrees within the interior angles of a decagon. Right? So instead of saying, all right, well, we're at hexagon, septagon or heptagon. They call them alternately, either one. Heptagon, and so it's 7, 8, octagon, nonagon, decagon. So 1440, or we could say 180 plus 7 times 180, 1440. One way or the other, you get. Now, if I tell you to do that for like a 37-sided figure, you're like, okay, this doesn't sound like much fun, but it's there is a relationship. When I said that there's 7 more sides than a triangle, there is something to that, right? So we're starting off with a triangle, number of sides beyond the triangle. Meaning if I have a quadrilateral, that's one more side than a triangle. If I have a pentagon, I have 2 more sides than a triangle, right? So if I had a decagon, I had 7 more sides than a triangle. But the relationship here is whatever number of sides I have, subtract 3, and that gives me the number of additional sides that I would need. So an n-gon has n sides, right? So it's like, all right, well, what do we do here? Because it's hard to say that it's like, what, 20 more sides than a triangle or 50 more sides? It's n, but what did we do before? We did 180 plus some number times 180. That number was the number of sides beyond the triangle, all right? But the triangle has 3 sides. That's why we subtracted 3. So number of sides minus 3, right? The 3 representing the triangle, right? The 3 sides of the triangle, right? So how would I write that? Well, if I'm telling you that there are 10 sides, I would do 10 minus 3. If I'm telling you that there are 100 sides, I would do 100 minus 3. But if telling you that there are n sides, right? So that would be the expression, and that gives us a rule. But most people, I mean, I could put this in parentheses, make it look a little nicer, but most people don't like the rule. They would rather just kind of think of it intuitively. The issue is when you get to numbers 11 and 12, now it kind of goes the other way, where it's like, all right, now that I know the interior angles in the polygon, how can I figure out the number of sides? All right, that makes it definitely a little trickier. So let's take a 5-minute bathroom break, or I guess I don't know why I said bathroom break. It could be any kind of break, snack break. Yeah. Anyway, a break, 5 minutes, and then we'll come back, and then we'll put the finishing touches on the lesson. Coming up with the number of sides, knowing the number of angles is a little bit of a different story. All right, so if we take this rule here, we could actually simplify it. We don't really do too much algebra here. We don't really need to, because it's not an algebra course. But this is one thing that I'm just going to show you the one time, and then we won't do it again, but because it'll be a rule from there on out. But we have this 180 plus n minus 3 times 180. That could be, by the commutative property, I could swap these two and make that 180 plus 180 times n minus 3. But then we could use the distributive property to run through with that 180 degrees. Right? I left the degree symbol off, but we'll put it back on later. right? Use the distributive property, and you get 180 plus 180 n minus 540. Right? Assuming, of course, that 180 times 3 is 540. Late in the evening, so you never know. But then I could combine some like terms here. I get the 180 minus 540, which is negative 360. So 180 n minus 360, what this simplifies down to. Again, just 180 minus 540, negative 360. All right. So this would be a rule where n is the number of sides. Right? So then all we would have to do if we want to find the number of sides in a polygon, we just take this expression here and set it equal to whatever the angular measure is. Right? So I would say, just kind of do a little side work. I would say 180 n minus 360 is equal to 2340. Right. Now it's basic algebra. That doesn't mean you want to do it. So it's really up to you what technique you want to use. I'm going to show you the algebraic approach, and then I'll show you something on Desmos. Right. But if you're doing it algebraically, you would add the 360 to both sides. And that gets you 180 n is equal to 2700. And then we divide out the 180, and that would give us the number of sides. And if it's not a whole number, then it's either a flawed problem or we did something wrong. Right, so that's going to give you 15. So the number of sides in the polygon would be 15. So this is actually a 15-gon. As dumb as that sounds, that's what it's called. Actually, any polygon can be called number of sides gon. So technically, I could call a triangle a 3-gon. Actually, another name for a triangle is trigon. Tri for 3, trigon. And if you've ever heard of trigonometry, the trigonometry, that trigon part is trigon. So it's the metrics of triangles. Right? So fun fact of the day right there for you if you're interested in that. But let me just show you on Desmos how you could handle this. Because Desmos is really good with numerical, well, with number crunching. I don't want to make it too fancy. So you could put a rule in any form. I could put it in the unsimplified form or the simplified form. If I type in 180 n, see it says add a slider, so I'll do that in a minute, minus 360, you tap on the n, and it brings up a slider, and that slider can be toggled to whatever you want it to be. All right. Now, the default setting is to go negative 10 to 10 in 10th unit increments. Right. So when we're talking about number of sides of a triangle, negative numbers don't make sense. Decimal values don't make sense. Fractional values don't make sense. Number of sides have to be what we call discrete values, have to be whole number countable values. Right. So what I would do is tap on the endpoint there. That's the thing. When you have a slider, you see where it says negative 10, you just tap on that or click on it with your computer and make the low bound whatever you want. Now, in order to be a polygon, the lowest number of sides you can ever have is 3, right? Because the definition of a polygon is a geometric figure with 3 or more sides that's enclosed. So a closed figure with 3 or more sides, right? But that's all well and good. If you think about having 2 sides or only 1 side, how could you ever close in a figure if they're all straight line segments? So you just kind of go back to what I did before. I have a point and emerging from that point in one direction is one line segment. I'll make it a line segment. And emerging from the point in another direction is another line segment. How could I ever have it be a closed figure? You know, the closest way I could get would be to have it one map over the other, but that wouldn't enclose anything. When we talk about enclosing, we're talking about enclosing an area. If I said find the area of this figure, you're like, well, where does it end? So area, like all of this and all of this, that, you know, that's not going to make sense, right? So it would have to have at least 3 sides in order to be a closed-in figure. Now, on the high side, we just saw that you could have as many as 15 sides. You'll see here, I mean, some angular measures, you got 2340, that was the one we just did, 1080. I mean, there's really no limit to the number of sides that you can have, but you gotta cap it somewhere. So I'll say 20, just to have a maximum value. The step is the increment. What do you want to go by? So I want to go by ones. So I'll tap into 1 then. Okay. So when I do that, I'm going from 3 to 20 by 1. So it's not going to take into account any decimal values along the way. Right. So if I slide my slider based off of this rule that we typed in, if I slide my slider to any n value, it's going to give me the corresponding degree measure for the sum of the interior angles at that location, for that number of sides, right? So if I'm looking at, for example, number 13, you're like, what's the number of sides if there's 1080 degrees in the polygon? I would just scroll around until I come across a 1080. And once I settle in on that, I would see that it's 8. Right? So I know now that it's got to be an 8-sided figure, and that would be my answer. The only issue with Desmos is that sometimes with touchscreen, when you try to slide a slider, it sticks. So it's easier to do with a mouse. But I mean, that's not bad, you know? So what I usually do, and I'll be doing this more and more as the semester goes on, I give it a little title, you know, a little notation here of what this gives. So gives the sum of the interior angles of a polygon. Finally figured out how to make that work, so I'm just thrilled. All right, some of the interior angles of a polygon, and then I save it. Sum of interior angles of polygon. And then I post that up on Blackboard, and then you'll have access to it. Right? It's very simple Desmos, but it's kind of nice. Right? And again, it works both ways, where if you know the angle, you just slide your slider until you come up with the angle and see what the corresponding n value is. Since n has to be a whole number, eventually you're going to find it. Right? And if 20 isn't big enough, like the degree measure is like 20,000 whatever, then just make this number bigger. You know, make it 50 if you want, and it'll allow you to keep going. Right? So that's a pretty cool attribute of Desmos. But it doesn't really help us with number 12, because if one of the interior angles in a regular pentagon, a polygon, they said pentagon would already be done, is 156, find the number of sides in a polygon. All right. So that goes back to what we were talking about up here. The sum of the exterior angles of a polygon is always 360 degrees, right? Now that may not seem useful at all, that piece of information, but it's incredibly useful, just indirectly. So let me go on back down here. I'm going to copy paste it in there. So the sum of the exterior, but you're saying, but they gave us one interior angle. Well, we know the relationship between an interior angle and an exterior angle. They're always supplementary, right? So if I just draw just one pair, right? So let's say, I'm not drawing the entire polygon because I don't know what it looks like. But if I just draw one pair of interior or exterior, the interior is 156. The exterior would have to be 180 minus 156, which would be 24 degrees, right? So if I want to figure out how many sides there are, and I know that there's 360 degrees as the sum of all of those exterior angles, and I know one of them is 24 degrees, then all I would have to do is take 360 degrees and divide it by 24 degrees. And that would give us the number of sides, right? So 360 divided by 24 would give you, 15 sides, right? So 15 sides. But again, we want to be able to generalize this, right? So in Desmos, you can make a rule because you think about what you did and what you want to do, right? So you have the interior angle, right? So what did we do? We took that number and subtracted it from 180, right? So if we call that interior angle, we call it whatever we want, we call it A for angle. What we did was and I'll just draw a side-by-side diagram here, just in more general terms. So instead of having 156, like some specific value, let's say I just had A degrees. Then what I would do is find 180 minus A degrees. I would get that answer and divide it into 360. Okay, so 360 degrees divided by 180 minus A degrees. I mean, that's what we did, as long as we know what A represents. Okay, so what I would say here is let A represent the measure of an interior angle of a polygon. Right. And so what I would do is then take 360. When you hit the division key in Desmos, it creates a fraction automatically. So we just got to kind of live with that. But we're dividing by whatever's in the bottom here. So that would be 180 minus A. And we create a slider for A. All right. So the measure of an interior angle, but it's still better than having it. Right. Now we think about what an angle could be in a triangle. Well, it could never be negative. So we'll start with that. Got to be bigger than 0. And it's got to be less than 180. They don't have less than here as an option. So I'll just use 0 and 180. But an angle could be a decimal value. I just don't expect it to be, but it's possible that it could be a decimal value. So I'm fine just leaving the step blank and letting it be decimal values if it comes up that way. So the thing is, when you have large enough values here, it won't give you a decimal. Like for example, if I made this 10 and left step blank, it would give me decimal values along the way. But when I make it sufficiently large, it has a little bit of trouble with that, right? So it defaults to whole numbers. But if I'm looking for the interior angle to be 156, I would just slide to 156. And it would tell me the number of sides, right? So if I can get it to stay on that 156. Now, if you have trouble getting it, like you see how I'm struggling here to stay on that 156. If you have trouble with that, you just tap on it and type it in, and it'll be fine. All right. But I would want to make a note, you have this expression here, you go to use it later on. What does that expression tell you? Well, we know that A represents the measure of the interior angle of the polygon. What I would say here is that the expression below gives the number of sides for given a particular angle, right? So the expression below returns the number of sides given a particular interior angle of a polygon. And it keeps hearing me pluralize angle, but that's not what I'm doing. So here we go. And so, yeah, now we have a nice Desmos here that could be used for a bunch of different situations. So, like we already did number 13 to some extent, where we would say, okay, we have the sum of the interior angles is 180. So I would scroll along until I come up with I'm sorry, keep saying 180, I mean 1080. So this would be n is equal to 8. Number of sides is equal to 8. Easy enough, right? Without having to do the algebra. If one of the interior angles of a polygon is equal to 180, then what's the number of sides? So I'd slide my slider to 180. It looks like 5 sides. Now we already did that problem, but still, it's nice to know that we have technology that will help us. So the number of sides is going to be equal to 5.